We're talking about 3.1 recursive definitions, algorithms, and the program. What you see here is the famous Russian Mashoshka dolls. You probably have seen it on the market or in YouTube or in television. Where you open up the doll, smaller one sits inside. Pretty much just peel the surface of the onions and keep peeling until you get to the smallest. What is this relevant to recursion? Recursion is a method of solving a problem where the solution depends on solutions to small instances of the same problem. Let's just move forward. The recursive definition is defined in terms of a smaller version of itself. So you can think of a drawer with a whole bunch of folders in it. When you start peeling the onions, you can see the contents within. And these contents are smaller than the previous versions that wraps around it. Another example is when you have a compound sentence, which is a sentence that consists of two sentences joined together by coordinating conjunctions. The other example is factorial. This is from your grade school. Factorial 2, for example, is equal to 2 times 1. And 3 factorial is 3 times 2 times 1. Generally speaking, you can express factorials in this fashion. N minus 1 is a recursive definition. Let's formalize this a little bit. Let's move on to the next page. Going back to this one example, calculating 4 factorial, we're starting with 4 factorials. And if you remember the equation says n times n minus 1 factorial. What this means for 4 is that you would have 4 times 4 minus 1 factorial, which is expressed herein. If you compute 4 minus 1, you get 3. So this leads to the bottom line here. 3 factorial itself is another computing card here. 4 factorial has a smaller portion of it, and this recursion is 3. If you move down to 2, you're going to see that 3 factorial itself is consists of 3 times 2 factorial. So if this moves on, we'll be calculating these cards. Each of these cards is responsible for the outcome of n factorial. So starting with 4, with 3, with 2, with 1. So in order to solve 4, we have to solve 3. And in order to solve 3 factorials, we have to solve 2 factorial, so on and so forth. So this is kind of like a top-down approach, right? You're starting with this baseline right here. Base case sits on top. And then as you kind of drill down into the individuals, sub-components, you go deeper and deeper until you get to the bottom, which is 1 factorial. 0 factorial by definition is 1. So you actually get down to 0 factorial to the bottom. This is a pretty famous example of using recursion to solve factorial problem in mathematics. You do not sometimes need to use recursion because recursion is pretty expensive. We'll talk about time and space later in the lecture. This is basically what I was illustrating earlier, that if you keep going, eventually you're going to have something like this. So 3 factorial is actually 6. And how do you get 6? Well, because you computed it from your recursion. One of the recursion is going to go straight into the 3 factorial. 3 factorial is going to go into 2 factorial. Once the program computes the very last card, which is what you see here, it bubbles up to the 2 factorial. The flow of control will just keep going back. At the very end, when you get to the base level, you will have the solutions in front of you readily. We're going to go into the Java representation of this 4 factorial program also in later slides.